Okay, so quiz Wednesday. It's kind of a hodgepodge, I feel like, of stuff. One, we have inverse derivatives. So that was on the website, those 10 questions on how to find the inverse derivative of something. And so remember that the definition of how to find an inverse. So g prime of b is defined as 1 over f prime of f of a. All right, that was the whole basis of that lesson and the video that you were to watch and what you were to get out of that. So there will be like a question about inverse derivatives. Okay, then the next hodgepodge thing we have is L'Hopital's rule. And indeterminate forms. So I'll give you probably a couple of those with different indeterminate forms. Maybe one of the indeterminate forms would be a subtraction and the other might be a fraction or something where you might need a logarithm or something like that. Okay, then the mean value theorem, which was yesterday. The mean value theorem is where you calculate the secant slope between two distinct points, and you set it equal to the tangent slope at a single, and find the single point that would be true at. So that's the mean value theorem, which requires differentiability as its strongest requirement, not just continuity, but differentiability too. Okay, and then the last thing are the derivative tests. And so we'll finish those up today. So you've got the derivative test, the first derivative test for maxes and mins, and then we're going to do second derivative also. All right, so that leads us up to 5.3. And so 5.3 are the different derivative tests. So what can you learn from the first derivative and the second derivative? So let's talk about the first derivative, which was last night. And we want to set the first derivative equal to 0 over 1 and 1 over 0. You're looking for both horizontal tangents and vertical tangents. So we've got to do that first. Okay, that first derivative is set equal to both of those things. Those are called critical points. Okay, so those are called the critical points of a function. All right, so how do you do your statements? How do you put it in complete sentences? And how do you, because you can draw the chart, but the chart doesn't get you any points on an FRQ. It's what you say in a statement. All right, so this is these are what you're gonna, how you're gonna say it. The function f of x decreases when f prime of x is negative, is less than 0. Okay, so it's going to say, over which intervals is the function decreasing? And you say the function is decreasing on such and such an interval because the first derivative was negative. Now you can tell that from your chart, but you summarize it in a sentence. And then you would do the same thing. The function f of x increases when f prime is shown to be positive, greater than 0. Your basis, your argument, for a function always has to be based on what the derivative did. You argue it for the function does this because the derivative did this. The function does this because the derivative did that. It's always an argument on the original function based on the derivative function. All right, then you ought to talk about extrema, maxes and mins. And so you're going to argue your case, the function f of x has a max when. Now here's where the reason often is weak. They'll say it has a max because the derivative is equal to 0. That is weak, that is insufficient. That's not true. Okay, Megan's exact argument today about tangent or cubic. They both have the derivative being equal to 0, but they don't have a max. So you can't say it's just when the function is equal to 0. It is when f prime changes from what to what? When would a function have a max? When the derivative is showing what kind of change? Positive to negative. That creates a max. Okay, when it's distinctly positive on one side and distinctly negative on the other. So do you see how it is not based on, nothing is based on being equal to 0. The converse about a minimum, the function f of x has a min when f prime of x changes the opposite way. All right. So if you ever cite being equal to 0 as the reason for anything, you'll get deducted points for being an insufficient answer. Insufficient reason. So those are the 4 things that you can tell from the first derivative. The increasing and decreasing behavior and the existence of a maximum or a minimum. So then the other derivative test is the second derivative test. It's a similarly the test is set up in a similar way. Okay, the second derivative test is also set equal to 0 over 1 and 1 over 0. To find, and these are called inflection points. All right, we haven't talked about inflection points yet this year. Yes, sir? No, not usually. It would be an inflection point if it showed up as a critical point. It would show up as a critical point with no change in the first derivative. Yeah, we call those stationary points. Yeah. Okay, so let me give you an example of a graph that has lots of inflection points. Okay, all right, here we go. Let's look at this. Okay, so we'll take a basic sinusoidal function. Okay, so it's got maxes and mins. You would argue the presence of a max and min based on the fact that the derivative changes at each of those points. Inflection points for a sinusoidal function are happening right here. Okay, those are inflection points. The value of the second derivative is equal to 0 there, and the change, there's a different kind of change that's happening. Okay, when you hit a max or a min, the change is happening in the direction of the function. When you hit an inflection point, there is a change as well, but the change is in what's called the concavity of a graph. okay? The concavity is a change in the steepness of a graph. Let's zoom in here. Okay, between the yellow max here and this inflection point, it's decreasing. But it's decreasing at a faster and faster rate. It's getting steeper and steeper as it's going down. As soon as it reaches the inflection point, it's still decreasing, but it's decreasing at an increasing rate. Okay, let's see. Max to inflection, decreasing at a decreasing rate. It's decreasing and getting steeper as it goes. From the inflection point to the min, it is still decreasing, but it's decreasing at an increasing rate. That means it's still going down, but it's getting less steep as it goes until eventually it's approaching 0 again. That is the change. It's where the rate of the decrease changes. So decreasing at a decreasing rate versus decreasing at an increasing rate. That is called concavity. So we call this section right here concave down. We call this section right here concave up. Decreasing at a decreasing rate, decreasing at an increasing rate. It stays concave up until the next inflection point. So this is still concave up. Sometimes we talk about being able to hold water, or like being a part of a parabola. You can almost kind of maybe visualize, I don't know if you can see that or not, like this section right here has sort of parabolic properties, and then between those two inflection points it has a different kind of parabolic property. These are not parabolas, but it has the property of being sort of like that. So you've got a concave down section, a concave up section, and then between the next two inflection points another concave down section again. This whole section is concave down. And then it just keeps going, another concave up section. A sine graph is a really good example of concavity. Kind of ask yourself, if it were a parabola, would this be a parabola that was facing down, or it would be part of a parabola that was facing up? You could do it on a cubic as well. Okay, here's a cubic graph. All right, the inflection point is happening right here. I'll do it green like the other one. Okay, here's another inflection point. If you can visualize the concavity of this side of the graph is as if it were a piece of a parabolic curve that was facing down. And then the concavity changes, and now you're part of a half of a parabola piece that's facing up. That is the change in concavity. So this section is concave down, and this section is concave up. Okay, so let's put some statements together. We say the function is concave up when, and you always base your justification on what the derivative, in this case the second derivative, is doing. And it's concave up when the second derivative is greater than 0. And then you're going to say the same thing about being concave down. The function is concave down when the second derivative is less than 0. Notice it's nothing equal to. Okay, we're never talking about equal to. Equal to is done in your scratch work when you're solving for critical points and inflection points, but in your statements, it's never equal. And then our final one is the function has inflection points when, and it's nothing, again, nothing to do with equality. It has to do with the change. When f double prime of x changes from either negative to positive or positive to negative, okay, when that change happens. Yeah. Huh. Thanks. All right, so let's actually do a question, and we're going to put this to the test. Okay, everybody caught up so far? Okay, so let's analyze a function without a calculator, and let's talk about what this function is doing. All right, so we are going to put all of this to the test. We're going to analyze the function x to the 5th minus 80x cubed plus 100. All right, so we're just going to tackle this. We're going to start with f prime. F prime is 5x to the 4th minus 240x squared. We're going to set that equal to 0. Normally we would also set that equal to 1 over 0, but as a polynomial, it's not ever going to be equal to 1 over 0. So we'll just set it equal to 0. We're going to factor out, what can I take out in common? Okay, 5x to the 2nd, leaving me with x squared minus, that works out to be 48. Which I can factor into x minus the square root of 48 and x plus the square root of 48. The square root of 48 can be simplified because it's got a 16 in it. So this will be x minus 4 rad 3 and x plus 4 rad 3. And so my critical points are 0 and plus or minus 4 rad 3. And so we would set up some intervals. From x less than negative 4 rad 3, between negative 4 rad 3 and 0, between 0 and 4 rad 3, and greater than 4 rad 3. So we're going to take our 4 intervals, and we're going to look for changes in the derivative. So since 4 rad 3 is the square root of 48, we know that the square root of 49 is the closest number to that, and so the closest whole number would be the number 7. And so we would plug in the number 7 to that and see what would happen, and negative 7 maybe. So if we plug in negative 7 into my different factors, we're going to get a positive number in 5x squared we're going to get two negative numbers in a row. Because if we plug in -7 here, here, and here, it'll be positive, then negative, then negative. And so this will end up to be, oops, positive, negative, and negative is positive. Okay, then we'll pick a number that's between -4 rad 3 and 0, like the easiest is -1. And so we'll plug -1 into each of those. We'll get a positive, negative, positive. So that would be a negative overall. We'll plug in the number maybe +1. That will give me negative again. And then we'll plug in the number 7 or 10 or something, and we'll get positive. And so you're looking here only for the places. We can see where it's going to have increasing behavior. We're going to see where it has decreasing behavior. But we're also looking for the places where we would see a change. And so we can tell that when it changes from positive to negative, okay, so Irene, right here, where it changes from positive to negative, is what kind of, what's happening in the original graph then when it changes from positive to negative? Okay, so is it a max or a min? Okay, so this is going to be the presence of a max, which means when it changes again from negative to positive, that would be the presence of a min. So we'll summarize that, and we'll say the function f of x has a max at x equals -4 rad 3 because, and the reason is always based on the derivative, because f prime of x changed or changes from positive to negative. And then we can say the converse of that for the minimum when we're changing the other direction. So the function f of x has a min at x equals +4 rad 3 for the opposite reason. Because f prime shows a change or demonstrates a change from negative to positive. And then Jerry kind of pointed out, what about 0? 0's got no change. We would call that a stationary point because there is no movement there in terms of a max or a min. Okay, that's looking at the first derivative. So let's move on and let's finish the second derivative so we can talk about the concavity. All right, so our second half of the question would be to find the double prime of x. So the double prime of the x is going to be 20 x cubed minus 480 x. Set that equal to 0. Again, we're going to factor. So I can take out a 20x. That will leave me with x squared minus how much? 24. And so when I factor, I'll have x minus the square root of 24, x plus the square root of 24. Set that equal to 0. And so then square root of 24 is 2 rad 6. And we'll have our potential inflection points to be 0 plus or minus 2 rad 6. So we'll do the same thing in the second derivative. So our intervals will have x less than -2 rad 6. We'll have -2 rad 6 to 0. 0 up to 2 rad 6, and greater than 2 rad 6. And we are going to check the concavity here. And again, you're going to pick something that would fall into that region. The square root of 24 is close to the square root of 25. So I'd probably pick x's. I'm probably going to use -5 here. I'll probably use -1, +1, and +5. Those are probably the numbers that I check. When I use -5, I'm going to get a negative number by 2 positive numbers. So that's going to be negative. When I check -1, I'll get negative, negative, positive. That's a positive overall. When I check +1, I'll get a negative number. And I check +5, I'll get a positive number again. So everything is changing here. So we can see we have 3 sections of positive concavity. Excuse me, 2 sections of positive concavity, 2 sections of negative concavity, and we have how many inflection points? 3, because there were 3 times where this changed. And so just to finish up, the function f of x has 3 inflection points, and those points are at x is 0 and plus or minus 2 rad 6 because, and it's always based on what the derivative or second derivative is doing. So the second derivative changed or changes nature. Or changes sign or nature or anything you want to say like that. Sign, you could also say nature 3 times. And you can also say what the concavity intervals are. So this is just a lot of analysis and putting this all together. So the quiz tomorrow, inverse derivatives, L'Hopital, mean value, and then these derivative tests. So that'll take like half the period. Okay.